Well, that was generous and embarrassing. Thank you very much. It has been such a lovely day. I have had such a wonderful opportunity to talk to just enthusiastic students doing incredible science, talking to faculty who I wish they were on my faculty. It's really just a lovely place. And as I told a few of you, I'm looking at real estate in Santa Barbara. So today I'll be talking about the adolescent brain, and much of my work is focused on this, largely with the advancements and imaging tools and technology. So we as adults can almost voyeuristically look inside the adolescent brain as that adolescent may be making suboptimal decisions and sometimes better decisions than either we could make as adults. And even though this technology has been around and there have been numerous studies about the adolescent brain and the functioning of the brain, I still to this day have colleagues, journalists, and family members and friends who talk about the adolescent brain in a way in which you would think we didn't have more data. They describe it often as a brain with a hole in the front, the prefrontal cortex, incapable of making rational decisions because the prefrontal cortex has been implicated in so many abilities that help us guide and regulate ourselves. And so really this analogy to a defective car, I find so insulting for the teenager, because basically saying that they have no brakes or steering wheel, just an accelerator, is suggesting they really can't engage in optimal behavior. And so this developmental stage has really gotten a bad rap in emotionally charged situations. When you make a bad decision, that's when they describe adolescence, and the adolescent brain is defective. But when a newborn infant can't talk or walk, or they poop their pants, we don't call that deviant, or we just call that development. So hoping this more positive idea about this is a typical stage that we all go through, and thinking about that. But the problem with overgeneralization, let me just back up and make a stronger point, and I can walk with this.
Yeah.
So I do a lot of juvenile justice reform work. And so I do talk about vulnerabilities and related to the immaturity of the adolescent brain, not in these derogatory ways, but it's a way in which when young people do come into contact with our legal system, to talk about how, yes, they should be held accountable for their behaviors, but we need to consider this in terms of diminished accountability with respect to who they are and where they are in development and what their experiences or their environment is. So I understand why sometimes my colleagues will say that they have no prefrontal cortex, so please don't judge them. They can't control their behavior, right? So many times it's in good faith or for a good reason. But the problem with that is, if we describe adolescence as not having self-control, not being able to make rational decisions, then that's going to limit the rights and the opportunities that we give them. Legal rights, medical rights for them to make choices about their medical care, and also opportunities in terms of leadership roles if we think that they can't regulate themselves or make good judgments and decisions. But then the other, where it's been a lot of focus of my time, is if adolescents are perceived to be deviant, then that can potentially bias judges and when individuals are being sentenced to more harsher sentences because they're viewed as more deviant. I like to think of the adolescent brain as adaptive. And so what I want to do today is to present examples of empirical findings based largely on psychological and neuroscientific data. And I want to sort of present these data to you, showing when adolescents can make good decisions or engage in adult-like or even performance that's above what we see in adults. But then at the very end, I want to just sort of pull together why the adolescent brain might be programmed the way it is. And I'll provide some comparative examples across species too, where we see it both in the human and in the mouse. Thank goodness there's some conserved circuitry, but that's definitely saying this is a stage when we're seeing different changes in that brain circuitry and in behavior. So a big question that I've had in my research is, why do adolescents respond to the world the way that they do? And today I'll just focus on the bigger discussion that I've described in the context of three basic questions. So the first is, what are the contexts in which we see adolescent behavior diminished relative to adults? And in what ones do we see it's adult-like or better? And then how are the changes that are occurring in the brain during this time, how might they help explain why we're seeing these different behaviors at different ages, from childhood, adolescence to adulthood, and across different social and emotional contexts? And then I'll briefly end, it's more speculative, but it's basically talking about how these behavioral brain changes may be just beautifully adaptive for the adolescent meeting all the demands on themselves at this time. How many of you would go through the early stages of adolescence again? Right? So many demands. Oh, God. Just wait, I've got a task for you. But really just thinking about how you're changing and the demands on you intellectually, socially, physically, sexually, all of those, and the way you're treated differently too, all of a sudden, just by changes in appearance. It's a lot to deal with. And so if we can already have some bias in the way that our brain is working, that can help us respond to those demands or learn from those experiences quickly, how that can not only help the adolescent transition into adult roles more effectively, or into a society or social group, but also their survival and the species survival. This one. Okay, so let me provide just a little bit of background before we start addressing some of those questions. The first is, I would just want to define adolescence as this transition period. It's really where the adolescent is now learning how to become relatively independent from the caregiver and the parent. It usually begins around puberty is the way we define it. Puberty is earlier these days. We can talk about 9 and 10 years of age, and it extends into the 20s. Now, in terms of the offset, my son has said, if it's financial independence, that it might extend beyond the 20s. And also just for some background, usually when people talk about adolescence and if an adolescent has risky behavior, they do focus on that region of the prefrontal cortex as if adolescents don't have a prefrontal cortex. We used to send them home with pictures of their brains to show their parents, yes, I have a brain in there and it has a prefrontal cortex. But basically, we focus on the cerebral cortex. But before I go to that slide, I just want to say this is a time of socialization and preparation for being an adult member of society. And so it's not surprising that we see that the brain is tirelessly provides to socially relevant information. So this is peers. These are incentives. Monetary gain can put you higher on a social hierarchy. And this is also threats. But we tend to focus on the cerebral cortex. So this is the most played developmental movie I think I've seen out there. Many of you have probably seen it. The areas that are turning blue are showing where the earliest significant changes in the cortical thickness are happening. And so I think it's a little bit clearer on the static image if you just focus on the second half. Basically, you're seeing the motor and the visual cortex are showing earlier changes. These areas allow us to see, to act. So we're seeing earlier changes there than we are in the prefrontal cortex, which allows us to use those abilities to guide our choices and our actions so that they're goal-oriented or abide by societal rules. I'm using that. So the thing is, there's a lot going on in the brain that goes beyond the cerebral cortex and goes beyond the prefrontal cortex. Although I hear this often, and it is a great cartoon. And I want to talk about one of the earlier studies out at Terry Jernigan's lab, where she basically showed in this glass brain, you're seeing where there's structural changes with age into the 20s. And so while you're seeing significant changes in the prefrontal cortex, shown here in fuchsia, you're also seeing peak changes in subcortical regions that have been associated with what we think about sometimes with the emotionality of adolescence, of desire and rage, fear, the fight and flight response. So they're changing as well too. So it's this work in imaging studies too, where we came up with this simplistic imbalance model of adolescence, basically making the point that given that we're seeing peak changes in emotional circuits at a time when prefrontal circuitry is continuing to show significant changes in a more slow-paced way, that if you're in an emotionally charged situation, then these emotional circuits will win out over the prefrontal cortex. And we also know from elegant animal work, Amy Arnsten has shown in emotionally charged situations, chronic stress and the sort, we have neurochemicals, like norepinephrine, dopamine. You can have high levels where they basically do the equivalent of take the prefrontal cortex offline. And that's why when we're stressed, we sometimes don't make optimal choices ourselves. This is exacerbated during the adolescent years. And so if I'm going to talk about when adolescent behavior or performance is comparable to adults or diminished or surpasses, I'd like to talk about some of the cornerstones of cognitive development. And that would be generally what I refer to as cognitive control, or this ability for us to inhibit inappropriate actions, desires, thoughts, and emotions that actually interfere with our goal-directed behavior, and particularly in the context of our behavior in the context of rules that are imposed and that the adolescent is learning about as they progress into adult roles and have to abide by societal rules. So one example of control that I studied is I focused a lot on impulse control. And yes, well, I think this dog maybe has impulse control. I think this cat just wants a hat. So, but I thought it would be good for me to allow you to perform one of our tasks, because many of the studies that I'll talk about build directly upon that. So you can think about how the individuals feel when they're performing the task. It's also in the afternoon. If you haven't had as much coffee as I've had today, you might be a little bit not as interested in the talk. So this is a go, no-go task, but to keep children entertained, but honestly, the adults like this task and even more than children, we put it in the context of whack the mole. So basically, the instructions are whack the mole whenever you see this mole pop out of your garden, but no, never press when you see this rare vegetable that pops up. Now, just a caveat, I grew up on a small farm in North Carolina. I know eggplants do not magically appear. Because my city staff and students created this task, it was just so entertaining. I haven't changed it. So what I'd like for you to do is to say whack as quickly as you can whenever you see the mole appear out of the ground. And I want to see how fast you go relative to New Yorkers and others who have performed this task. As always. So are you ready? Yes. Okay, and it's a sneaky mole. All right. That was a little bit slow. Okay, let me start over.
Whack, 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 whack.
Okay, now let's see how your performance compares to children. And basically, what you can see, this is just a go, no-go task. Individuals are plotted based on their performance, but by the mid-teen years, we're basically seeing that their performance appears almost adult-like. And we're seeing that there's some teens that are outperforming adults. And some of us in this room might be out here in terms of. Okay. So tasks like this, you can have very simple working memory tasks, or what we use in the lab like digit span, where you're given a series of numbers, right? You give them back in reverse order, or the fluency task where you're given a letter like F or A or S, and you try to generate as many words as you can. Using tasks like that over hundreds of individuals and across many studies that I'm not showing now, but across this one of almost 1,000 participants. Again, you're seeing this asymptote sort of leveling of the performance by the mid-teen years. And this is cognitive performance. And I've also already mentioned that during adolescence, there's this heightened sensitivity to the social world and social information. And so it's also been the case that psychosocial abilities have been plotted. These include self-reports on likelihood of engaging in sensation seeking, riskiness, influenced by peers, and the sort. And we see that it's has a later developmental period that extends well into the 20s. And these psychosocial abilities actually include two different processes that I want to talk about. One is sensation seeking or construct, and the other is self-regulation. So sensation seeking is peaking during adolescence. We've already talked about how a number of changes in emotion-related circuitry are showing peak changes during this period. But then we're seeing our ability to regulate ourselves in these situations in which we're experiencing sensation or emotion of the sort is showing this protracted development into the mid-20s. Just talking to the students earlier, it's also important because there's a lot of blowback in terms of we have created adolescence in Western civilization. So I like to present cross-cultural data. And basically you get the same pattern that I showed you before across these different cultures. So now what I'd like to do is to, again, think about impulse control, but let's think about impulse control and how monetary gain, peers, and threats can influence. Impulse control can influence decision-making and other behaviors. But I need to illustrate first the pattern that we're seeing in response to monetary gain or threats before we can combine those with impulse control and even peer influence. So one of the first studies that we performed, it was Adriana Galvan at UCLA, phenomenal professor and dean at UCLA now. We got really tired of hearing people talk about how adolescents could make good decisions. And so we wanted to look at how are adolescents processing rewards that can sometimes be related to risk. And since we were interested in rewards, we wanted to build on the beautiful work by Wolfram Schultz and many of his colleagues, where they looked at how the dopamine system and dopamine neurons are firing in anticipation or receipt of reward, manipulating the probability or the magnitude of the reward. So the task that I'm going to show you is one that builds directly on what Wolfram used, looking at magnitude, but I'll mention probabilities later, where all the animal had to do was to say what side of a screen a stimulus occurred. He did not use pirates, as we did. The screen goes blank, and then they're given a cue to say which side of the screen it appeared. Simple task. Children, adolescents, and adults are almost at 100% accuracy. Now, in this study, just like Schultz did, we had 3 stimuli that were associated with different magnitudes, small, medium, and large. This was unbeknownst to the participants. I will also say we're using these abstract coins because when we had numbers, the adolescents turned this into a mathematical working memory problem where they were calculating how much they were going to earn by the end of the game. So we had to use abstract cues like this. If you look at performance on a task where you're manipulating the probabilities of the reward when you get that particular trial correct, and if you're manipulating the magnitude of that reward, what we see is over the course of the experiment, from the beginning to the end, what happens is the pirate that's associated with a small coin, response times to simply say what side of the screen the pirate was on, they get slower and slower. And our response time to say what side the pirate was on when that pirate was associated with a lot of coins ends up getting faster and faster. Now, in the title of the slide, I talk about how cues can drive behavior even without our conscious awareness, because at debriefing, handful of participants said, I think there were some pirates that were associated with me getting more coins. But then when we asked them specifically to tell us which of those pirates was associated with the biggest magnitude and the smallest, they could not provide that information to us. So we were talking about free will and determinism in terms of our behavior in action. Sometimes we're not even, well, earlier we were with students, sometimes we're not aware of what's changing our behavior. We're not consciously aware. So always think about that question too. Now, the big question we had was, how does reward, how is that represented in the brain across development? And this was the big finding where usually people had compared adolescents and adults, but this study really looked at how the brain is responding to the magnitude of reward. And we see this specific adolescent specific effect. So they're activating more to the large reward relative to the smaller reward. And this is a finding that's been replicated across labs around the world. I'll just show you one more. This is from Evelyn Kroon's lab in the Netherlands. Over 250 participants. They each had longitudinal data of at least 3 scan points. And you see this adolescent specific pattern again in terms of the magnitude of the pattern of activity. Does this look reminiscent of anything? It looks reminiscent of the sensation seeking, right? In terms of that curve too. Now, the reason why I'm showing you this slide is, what does it matter that they're sensitive to rewards? How does that play out in real world behavior? So we gave a survey, actually, a survey that Steve, who was here in the audience from NIDA, had recommended that I use in this research. But we wanted to look at the likelihood of engaging in risky behavior. And those individuals who endorsed in this early study, endorsed that they would have the likelihood of engaging in the most risky behavior. And this can include anything from leaving a party with a stranger to engaging in sports, you know, like rock climbing could be one of the more risky types of sports. It included those so that we could get risky behavior. Ask the questionnaire to all age groups. So we're seeing this associated with risk. But sensitivity to rewards is not only about risk. And there have been a number of wonderful studies, one that I'll just point out. And it's by Julia Davido. And basically, what she showed is that adolescents have enhanced probabilistic reinforcement learning. So what do I mean by that? The adolescents were quicker and persistent in picking up on optimal choices when you had probabilities of a reward. So choices that are associated with 80% probability of reward versus 20%. And it's not just that they can pick up on these probabilities of reward. It's also the case that they can shift and they recognize when these reward contingencies change. So this is just showing you another peak where adolescents have more proportions correct because they're exploring once the payoff is not what they thought it would be, and now they're shifting and finding another solution and seeing that their reward, the highest probabilities are associated with a different choice behavior. Okay. Another example, I won't call it a reward, but an incentive. Like when you're giving talks like this, you usually sometimes focus on the person who's smiling throughout your talk or nodding their head, right? So these social cues, even here, this is just a static image, but we wanted to see how do they play out in terms of performance by teens to perform impulse control tasks like the whack-a-mole test that you did. And so first, since we're using social cues, I want to show you both of these cues. One's just neutral, and the other one is this happy smiling face, like there's approval. And if we look at the number of false alarms, that is, they go when they've been told specifically not to go, we see regardless of the cue, children are making more errors than teens who are making more errors than adults on this task. Again, this is combining both these cue types. And if we look at the area of the brain that's correlated with their accurate performance, not when they're making errors, but when they're actually able to get it correct, we see that the group who's having the most difficult time when they get it right, they're recruiting this right ventrolateral area. It's an area in animals and humans. If there's damage or you lesion this region, it can impact your ability to engage in response inhibition behaviors. But we wanted to understand what types of errors adolescents were making. And so remember, adolescents are making fewer errors than children. But if we look at the difference in errors to the smiley face relative to this neutral, we see that the majority of the errors that they're making are not being able to stop themselves from going to that happy face. And you don't see that pattern in the children or the adults. So again, specific to this positive performing context or social. And then again, if we look at the brain when they're performing this task in the scanner, we see the same pattern that is in the nucleus accumbens in humans. Really, I should be saying ventral striatum. But in the nucleus accumbens, which we usually associate with the rodent work and the less complex ventral striatum that we see in human and non-human primate work, we see elevated nucleus accumbens activity, these positive social cues. The same area that I was showing was sensitive to receive the large reward in monetary gain. So what I'm showing you is there's exaggerated behavioral brain responses to positive social cues during a time when the prefrontal cortex is still showing changes in development. The prefrontal cortex and this pattern can't explain why adolescents do what they do, because the prefrontal cortex as children is even more immature, right? And so this is how we came up with the imbalance model in terms of these two systems and their interaction and which one they went out. All right, I showed you these social cues, but really, I can't give a talk on adolescence without talking about the adolescent psychologist Larry Steinberg's work. He's done a lot of work on peer influence, on teen decision-making. And I love this task, and it's a game we've all played, and that is, do you or don't you go through the yellow light? And I know many of us have gone through the yellow light when we probably should not have, but we had our reason. But the beauty of this task is you're trying to go through a series of intersections as quickly as you can. If you crash, then you have to wait there, and that's going to add more time to you finishing the task, and the goal is to finish it as quickly as possible. But the beauty of the study is he had individuals perform it alone or with a peer present. And then they actually measured how many risky decisions were made and also how many crashes were made. And so I'll present the risky decisions as a function of different age groups and the number of crashes. I want you, if you can, just to focus on the blue bars first, because it's important if you're looking at peer influence to see whether or not there are differences in the baseline task without the peers present. And what you can see in the blue bars is none of those are significantly different from one another. So even the young ages are good in their performance about whether to go through a yellow light or not, even though they have less driving experience. However, where we're seeing the biggest effect is right here when the peer is present, right? So this is when the teens are inclined to engage in more risky decision-making and going through the yellow light at a time when they probably should not. And when we look at when they're making that risky choice, when they're in the presence of the peer, again, we're seeing the same area of the nucleus accumbens, just as we've seen with monetary gain and those stagnant social cues. In contrast, the areas of the brain that the adult are activating, whether they're with a peer or not when they're performing this task, is in the lateral prefrontal cortex. So again, this is the performance, but we're really seeing the risky behavior driven more by these subcortical regions that are showing few changes during the adolescent period. Okay, again, because of the blowback with that we've created adolescence, it doesn't really exist. I think it's important not only to look across cultures, and I will admit with the cross-cultural study, if you look carefully, it looks like most of those were urban and not rural, and that can play a role too when you look across different cultures. But Steinberg collaborated with a neuroscientist, and they began to develop cohorts where they could look at the presence of a peer where they got along and could be in the same cage. And they wanted to look at how much drinking time they spent with ethanol or alcohol. So when he told me about this study, I was just like, well, that's a lot of time. I'm not sure what the payoff's going to be. But let me just show you when the juvenile and the adult are alone. They spend time at the nozzle where the ethanol, the alcohol is being released an equal amount of time. When the juvenile and the adult are with a cage mate, you only see a greater time spent with that nozzle where the alcohol is in the juvenile. Just an aside. Right. So I've been focusing on positive, peer effects, risky behavior. But I think it's important for us to talk about threat and stress, particularly given there has been this rise in anxiety and stress-related disorders, and that increase was even happening before the pandemic. And so let's see what influence threat and stress has on people. And while I don't think that you're afraid when you see this picture, what it is a cue of potential threat. When you see somebody with a fearful face, we've learned to associate that with a potential threat around us. So with these potential cues of threat, we wanted to see, is the adolescent fearless or are they fearful? And how does that impact their ability to stop themselves or go? And so what we saw is the teens were really reactive, but I don't like to say they were drawn to danger, but very reactive when they saw those cues of potential threat relative to the neutral cue. This reactivity could be when there's a potential threat, you want to activate the fight or flight response very quickly, and being reactive could be allergic to responses like that in that system. And then if we look at the neural correlates of this behavior, again, we're seeing adolescent-specific increase in activity in the amygdala, a region that's so important in learning about the emotional significance of stimuli in the world. But here's something else that I want to mention here. It's not just the magnitude of the activity, but when adolescents get revved up, it's hard for them to let go. So if there's a potential cue of threat, they continue to show a response to that cue long after the threat is possibly gone. And if it stays on even longer, that can be pathological. And we've seen that that's associated with different anxiety and stress-related disorders. So let me just illustrate that to you in a simplified movie. I mean, it's not like what we get at the but an example of an adult and an adolescent. When they're seeing these cues of potential threat, this is an adult. So cue of potential threat, you would expect there to be some sort of response in trying to interpret it, but nothing bad is happening to the individual, nothing good either. Eventually, the amygdala goes back down to baseline. And that's shown in blue. Now in the adolescent, we see the exact same pattern in terms of when the cue is presented, we see the response is activation of the amygdala again to that cue, but then it keeps going and going, and this activity continues to persist. Individuals who endorse high trait anxiety, what you actually see is over time, the activity increases as opposed to decreases. And so that's been a marker of some of what we've been seeing in some of our more clinically based studies. I always like to say the problems with my studies because sometimes that leads to even more interesting studies for me. But if we're comparing children, adolescents, and adults, and we're using emotional expressions, just by the mere fact of the number of years you've been on the planet, you're going to differ in your exposure to faces and facial expressions. So really, this is not the best type of stimulus that I can use. But what we can do is we can take a neutral stimulus and associate that with something aversive, and that would be classical fear conditioning. So I just want to talk about these classical fear conditioning studies. As you all know, basic psychology, right? You can pair a tone with a shock just a few times. And this will lead to freezing behavior. If you put the animal in another environment and play that tone, freezing behavior. When they hear it. The important part of this task that I want to underscore is the extinction. That is, because we see adolescents showing this persistent response to cues of potential threat, I want to know, do mice and adolescents show a persistent response to a cue that they have learned? So you would want to test it with extinction, where you don't have the aversive shock repeatedly. In children, we don't want to shock them. So we play this loud aversive noise. It's like chalkboard and static back in the old days for older individuals like me, when you wanted to hear that critical score, the game, and you're traveling and all of a sudden you just lost it. It's just like the aversive, and you get a galvanic skin response that shows individuals are more arousal to it, and they also rate it as very negative. And so again, there's fear acquisition when you pair that tone to one of these colored squares. And then you can assess the learning by comparing that GSR response to the condition equivalence. That was the pairs and to the one that was not. And then you can extinguish it by continuing to present these bars with no aversive sound. So first, let me just show you the acquisition data. This is interesting, and I don't think it comes as a surprise that children can very quickly learn to associate a cue with something aversive. You know, a hot stove, they learn about very quickly when they experience that pain. But again, our question was, once you have an association like this and you trigger that fear response, how well can you then extinguish that fear response? And what we observed in both mice and humans, and this has been replicated in rats and in other labs, we basically saw that adolescents show less cued fear learning. So the less cued fear learning, the reason this bar is low is because we're looking at differential and freezing. In the mouse, we're looking early to late. In the human, we're looking at that differential galvanic skin response to the conditioned stimulus for the one that's not. And we're seeing very little difference. So they still have a high freezing. They still have a large galvanic skin response. Now, that's cued fear. So they do look fearful, even though they're often described as fearless, where they think they'll never die. People have described them as never die. There's actually surveys that show if you ask them the likelihood of them getting sick or a fatal disease or something like that, they rate themselves much higher than older ages. So they do think that they're vulnerable. But let's also look at another type of conditioning. Rather than the cued fear, let's look at contextual fear. And so simply, you're shocked in a conditioning chamber day one. The next day, the mice are brought back and they're put in the conditioning chamber. And really the question is, will adolescents be more fearful? Or what will we see based on what we saw with the cued fear? And adolescents look fearless. Put them back in that conditioning chamber and they don't freeze. I mean, as Francis Lee and Siobhan Powell, the graduate student who was working on this in a test, we sat there and said, are they stupid? They were just shocked and we shouldn't have said that about the animals. That was, sorry, derogatory. But yeah, we were just really blown away by this. They have to be learning. They're such good learners. I've already talked about how good learners they are. And so for the graduate students in the audience, Siobhan had all these video recordings. Is anybody doing infant work or videotaping where you have to score them? It is hours and hours and days and years where you're coding. And so Siobhan wanted to graduate. So she wanted to try out this automated software that could tell when the animals were freezing or not. And so She went in and she got a random cage of adult mice and she put one in the conditioning chamber and it froze over in the corner. Let me try another animal. She pulled another out of that same cage, another adult, and it was trying to get out of the conditioning chamber. Her first thought was, darn it, somebody hasn't cleaned out, like in, the chamber. There's residual of fear. She cleaned it out. She brought another adult animal from that cage and put it in. And again, it was freezing in the corner. She then went back and looked at the notes on the cage. And these adolescents who showed no fear when they were put back into that conditioning chamber, those same animals, when they're adults, they're showing as much fear as these animals who were conditioned the same day. Isn't that wild? I know, it was wild. And it was all about just trying automated software. Usually some of the coolest findings were serendipitous.
So you're saying they remembered from earlier?
So they had learned, they weren't stupid, bad me. They had learned, but they weren't expressing it. So what I'd like to do is to turn to, I talked a little bit about reward circuitry. It's just sort of a brief primer on fear threat circuitry that's conserved across humans and mice. And then I'll talk about developmental changes that we think might explain what I think are opposing behaviors where they look like they're fearful to cue fear, cues of fear, but in different contexts, they look fearless. Did you have a question for clarifying? Okay, just post to me.
Hold your question.
Okay. All right, so how might developmental changes in the brain help explain these behaviors? So ever so quickly, just a primer for many of you, the amygdala is very important in expressing fear. Usually there's sensory input, comes into the basolateral amygdala, and it's going to interpret the emotional significance of that cue. The projection to the central amygdala is key in us feeling that fear. It projects to the autonomic nervous system. It can turn on the fight and flight response. The prefrontal cortex in the mouse, infralimbic in human, ventral medial prefrontal cortex. If you lesion it, you interrupt fear extinction. And so this is the fear extinction. Again, circuitry is oversimplified for you, or just a quick refresher. There's another area of the prefrontal cortex, prelimbic cortex. This area is associated with maintaining fear. Look, there's situations where we should be afraid and we need to maintain that fight or flight response and be able to respond. So basically I call this like the ever ready bunny, that ad where the bunny just goes on and on and on. This is a recurrent loop. And so you're continuing to maintain that activity through this recurrent loop. And then I just talked about context in which we should be afraid and we should be, activating any circuitry in the body that's going to allow us to respond to that threat for our survival. And that's going to be the hippocampus, which plays a huge role in contextualizing threat. And so the hippocampus has a direct projection to the basolateral amygdala. Again, that can help activate this recurrent loop, but importantly, then you have this excitatory projection to the central amygdala. That's going to lead to the fear response. But the hippocampus can also dampen the fear response. There's a projection to the infralimbic and the prefrontal, right? That's going to shut down the fear response. But we also know that there's projection to this prelimbic area, and it can gate the activity in this region. It can actually inhibit it. And so that would lead to, if there is a bear outside the tent, you really want to activate the fight or flight response. If the bear is in the zoo, there's no need, right? There's no real threat there. So now, how is this circuitry changing specifically during adolescence? And we know from the original Papal study that showed that the mice they had diminished fear extinction, and we also showed in humans that they had diminished fear extinction during adolescence. In that study, we show that they're activating the prefrontal cortex less during extinction than the adults are. And there have also been human studies looking at immature patterns of functional connectivity between the amygdala frontal activity. But there's another pattern that we've seen based on mechanistic animal work, looking at tracing studies. And what you see during adolescence is a surge in projections from the amygdala and from the hippocampus. So let me unpack this. If you have a surge to the prelimbic cortex, that's really like you've fired up that ever-ready bunny, and that's just going to send this loop going wildly in time. And so if that loop is continuing, then it's going to be hard for you to shut down that fear response. So I've shown one pathway, but here's another way in which it might help to explain this diminished huge fear extinction that we see in adolescence. And that's what I describe here for you. Increased inputs from the amygdala to prelimbic. Keep this recurrent loop active, and that might explain why they can't shut the fear response down during fear extinction. But what about this projection from the hippocampus to prelimbic? This can shut down this loop. And even though they've learned the fear as an adolescent, and we know they've learned it because they show it as adults, every time it starts up, it can get shut down through this projection, potentially from the hippocampus to the prelimbic. So again, to say that in different words, increased inputs from hippocampus to prelimbic cortex can lead to dampening of this. And that might be associated with them looking fearless and showing no contextual fear. Why would the brain be programmed this way then? Why? If something bad happens to you in a situation, would you want to go back to that context or show no fear in that situation? Why can't you let a fear association or fear memory go? Why are we so influenced by peers and incentives? So I want to just speculate and provide some possible ways in which this can be adaptive if we think about this from an evolutionary developmental framework. The sensitivity to incentives, rewards, and peers may actually motivate learning and exploring to find new resources. Food is going to be rewarding. As we get bigger, we need more resources. We're going to have to explore and find other places where we can get that food and water. It's also the case that if you're lucky enough to be in a home where you have food, water, shelter, clothes, clean clothes, and all the other things that we have, you need something to pull you out of that environment. Because otherwise, why would you go? And it's going to be important to be pulled out of that environment if you think about continuation of the species too, so that you can have successful mating and continuation of the species. Now, if you go out and explore and learn all about the wonderful things in that environment, potentially find mates and the sort, if you go out there and a predator comes and takes you out, you're no better off having gone out there than stayed at home. And so we think that's why there's a mechanism in which when you think there is a potential threat, you no longer have the caregiver to protect you. You have this persistent vigilance of that threat being out there. That might be very important for survival. And then a lack of the contextual fear during adolescence that might help you when something bad happens. Instead of staying home, you continue to go out and explore, again, helping to gain the resources that we need, food, water, shelter, but also in terms of the species, the mate. And then since we're talking about mating, being able to remember where danger is when you're sexually mature, as you become the parent, the caregiver, it's important that you have mechanisms in place that may prevent you from then nesting or having your offspring in that dangerous location. So, while the adolescent brain is often described as defective, I think that it's really beautifully evolved to facilitate learning. It's involved in ways, I didn't take the opportunity to talk about some exploratory studies where they look at exploratory behavior in adolescents specifically. But I think these are mechanisms that not only help the survival of the adolescent, but also the survival of the students. So I just want to thank the many institutes that have funded my work over the years. Usually I have a picture of all my, and thank the Sage family. Usually I have pictures throughout my talks of my mentees throughout, but these are collaborators and the majority of them are mentees, including Kylie, who's here. And then I always like to thank my son who gave me a very fit and novel way of viewing the adolescent period as he went through this time. So I'm indebted for my view of adolescence in large part based on my interactions and viewing him. So thank you very much.